where 1.8% of all global emissions, which
Okay.
in the grand scheme of things is huge, isn't it? So this
right.
is where
Okay.
the production side of it you can then decarbonize, and that's
Okay,
what
so
makes
that
it
means
green. Fertilizer is 80% of the uses of ammonia.
Yeah.
But there's new applications now, which is where the green side of it comes in.
Okay.
But the great thing is that the world's almost set up for us to use ammonia as a decarbonisation source. With hydrogen, you need a very small amount of energy to cause an ignition.
We're sitting in this room,
Yeah.
and then we get ammonia leak here.
Yes.
So that means like, how much is dangerous to us? Well, these are the sensors that can do the hearing, the seeing, the smelling.
Exactly, yeah. They all have their own purposes.
Yes.
Should we dive in?
Please.
Yeah.
Without ammonia, life as we know it today won't be possible. It's good for plants, fertilizer, energy transport. Ammonia is great, but too much of it is actually pretty dangerous. That's why we need to handle it safely, and that's exactly what we're going to be talking about today. And Hyfindr Tech Talks with an expert in this field. He is a person who has done a lot of research in hydrogen production and fuel cells. He's an engineer, has a postgrad in renewables, and now takes care of everything related to ammonia and hydrogen at MSA in terms of sensors. Welcome to Hyfindr Tech Talks, Jack Samways.
Thank you very much, Stephen. How are you?
Great to have you.
Thank you very much.
Yes, and always good to talk to you about these things.
Absolutely.
So let's start straight away. Jack, what is ammonia?
Well, it's a very simple compound. It's nitrogen and hydrogen. It underpins industries worldwide.
Yes.
And its next role is decarbonisation. So
Right.
that's what we're here to talk about.
Okay.
The green ammonia.
Okay, green ammonia.
Yes.
Okay. So why is ammonia important at all, to life, to hydrogen?
It's just incredibly versatile.
Yeah.
You can use it in so many different industries. You can turn it into ammonium,
Yes.
which goes into fertilizer. So I think fertilizer is 80% of the uses of ammonia.
Yeah.
But there's new applications now, which is where the green side of it comes in.
Okay.
Producing it from green electrolyzers.
Okay.
But traditionally it's made from steam methane reforming.
Okay.
So it
So-
accounts for a lot of global emissions, 1.8% of global emissions.
So the making of ammonia
Yes.
counts for
So
carbon
that's
emissions
where
already.
It's carbon intensive.
Okay.
And that's where there's the key part to decarbonize.
Okay. So let's look at a bit of a flow, which you
Oh,
brought
yeah, of
here
course.
for that. And can you just take us through what we see here?
Of course. So traditionally, natural gas reforming is how ammonia is produced. It's obviously very cheap.
Okay, that's here. Yes.
So this is the flow path traditionally, and that then creates hydrogen. Then something called the Haber-Bosch process creates ammonia, which
Okay.
effectively just heats it up and
Okay.
combines that with nitrogen to enable that to bond and make that compound of ammonia.
Okay. So it takes obviously nitrogen from air. Air is,
Yes.
I think, is it 78%?
Exactly,
so
yeah.
there's a lot of
Yeah,
nitrogen
right,
already
in the
around
air
us
right now,
here.
exactly, yeah.
And then, so in this Haber-Bosch process, you combine the
Yes.
nitrogen from the air and the
And hydrogen,
Yes,
and
yeah.
make ammonia from that.
So what you're saying is to actually get this started, you need hydrogen. You're starting from
Exactly,
hydrogen.
yeah. So this
Right.
is where
Okay.
the production side of it you can then decarbonize, and that's
Okay,
what
so
makes
that
it
means
green.
so if you get the hydrogen from renewable sources,
Yeah, so
like
this is green and this
yeah.
is traditional ammonia.
Okay, and this is obviously from crude oil,
Yeah.
petroleum,
Yeah, natural gas.
and natural gas. Yeah,
Yeah.
sorry, and that's making that causes all these CO2
Yeah,
emissions,
this is
right?
where 1.8% of all
Wow.
global emissions, which
Okay.
in the grand scheme of things is huge, isn't it, when you think about...
And I mean, I know that ammonia is used in a lot of places.
Yeah, so as I say, traditionally the most 80% of it goes
Yeah.
straight into fertilizer. So fertilizer
Fertilizer, okay.
is then used obviously for the agricultural industry.
Yeah,
So
okay.
as you mentioned, it's really important to...
So that's the point where I said life as we know it today.
Yeah.
because- and I saw a statistic that at least a third of us wouldn't exist because there wouldn't be enough food.
Exactly, yeah.
So this has been called feeding or making fertilizer from air process.
Yeah,
and
so-
it's enabled humanity to
Yeah.
develop as far as we get today.
Of course. But then also, pharmaceuticals, polymers, refrigeration. This makes up the 20% outside of fertilizer.
Okay.
So these two industries, the traditional applications.
Yes.
But as I mentioned, what we can do is we can produce it from green hydrogen, so electrolyzers, we're using renewable energy, like solar and wind.
Yes.
And then also what we can do is use these new applications.
Okay.
And these are using hydrogen as a carrier, an energy source, so using actually burning the ammonia in engines or using it as storage. We can go on to it later on, but there's some really benefits when it comes to using ammonia as storage.
Okay, so that means that you can, so from the, basically go backwards in this process. So the hydrogen that you made here,
of course.
and then transport that again.
Yeah, so this is called the Haber-Bosch process when you combine them.
Yes.
And it's called cracking. You can crack
when you go
ammonia back, so you reverse the process.
So
what you could do is, if you were trying to get hydrogen across, because ammonia is really set up to be transported globally. There's import terminals all over the world because it's such a common gas.
Yes.
And so everything's there to be used as a carrier.
Okay.
So what you can do is you can transport ammonia over to another country, then heat it up and then crack it back into hydrogen.
So when it's created, is it a gas or is it a liquid? So what are the ships carrying?
Yeah, so you can have either. You can obviously leave it as a gaseous ammonia, or very easily you can turn it into a liquid ammonia.
Okay.
As we know, as mentioned here, I don't know if you can see that, to create hydrogen into a liquid, you need to cool it to minus 253 degrees, which is an incredible energy-intensive process to cool it down that low and also maintain that temperature. But what you can do is you can cool ammonia to minus 33 degrees to cool it into liquefy. Or what you can do, if you leave ammonia at room temperature and then pressurize the 10 bar, you can liquefy it very easily. So you can transport it around at room temperature at 10 bar as a liquid. So that makes it really a small amount of energy required to transport it as a liquid ammonia.
So just coming back here, you make it here and then you can easily liquefy it.
Yeah, easily liquefy.
Transport it
10
to
bar,
somewhere.
room temperature, transport it across.
10 bar, room temperature, okay.
Yeah.
And then start doing whatever else you want to do,
Yeah,
either fertilizer or back to hydrogen.
So if you're trying to transport it right across and it's being used in trucks or heating or...
But you can't use the ammonia directly in the vehicle, no?
Yeah, you can.
You can.
But then it's, so the shipping industry is looking ammonia as a cornerstone to decarbonizing that industry too.
All right.
So either using it, putting it back into hydrogen and putting it in a fuel cell, or using ammonia directly as the fuel.
In the ship.
Yeah.
Okay. Yeah.
So
actually, the ships can also transport the ammonia and then use some of that ammonia to power them.
Yeah, potentially. I think it's more the case that it's either transported or used as a direct source. So I think it's either one or the other. But so especially in the Nordics, they're looking very seriously at ammonia. And there's a lot of pilot projects.
In those ships, the ammonia obviously will be cracked back to hydrogen and used in either fuel cells or
used directly as ammonia. So
it can also be used in the engine directly.
Exactly.
I think we need to do a separate tech talk about that one.
Maybe get a shipping guy in here.
Yeah. Okay, let's quickly look at some of the differences between hydrogen and ammonia, because I know we talked about that.
There is a lot of differences to this, mainly around the toxicity. So ammonia is a very toxic gas.
Yeah.
So that's what you mentioned about. You mentioned about too much, maybe for us too much. Obviously, ammonia is useful very much in the industry side of it, but we can only allow a very small amount. So 25 ppm is the limit across 8-hour period.
Okay, so that means one clear difference: ammonia, that's the green side here.
Yes.
And hydrogen.
The bottom is hydrogen, and the top is ammonia.
So obviously toxicity. Hydrogen not toxic.
But very flammable.
Well, very flammable. Yeah.
So as we know,
that's this one. Yeah. Fire. Okay. Mm-hmm.
Yeah. So with hydrogen, you need a very, very small amount of energy to cause an ignition.
Yes.
And has a really wide flammability range. So 4 to 77%. Whereas ammonia has a much smaller window where it's flammable.
Okay. You mean in terms of concentration?
Yes, concentration in a room like this right now. So hydrogen very explosive, under the right conditions when it reaches the low flammability limit, and if an ignition source occurs. Whereas ammonia, very, very small amount. So as I mentioned, at 4%, hydrogen becomes flammable, which is 40,000 ppm.
Yeah.
Whereas ammonia really is dangerous to us even as low as 25 ppm. Okay. So the difference in terms of like when it's harmful to us is they're very, very different gases.
Okay. Okay. And we have here propensity to leak and corrosive gas. Yeah.
So ammonia can be very corrosive to certain metals,
whereas
hydrogen's a very, very small molecule,
yes.
so it can leak through many cracks. I'm sure people know about.
Exactly.
We've covered hydrogen
we've covered
leaks.
that, exactly. We have other videos about that as well, and actually, leak detection and leak-proofness.
Well, we're going to discuss that today, so campaign.
So ammonia is already widely used, as we already mentioned.
Very, very common gas. So it's it's an industry we've been supplying for decades and decades. So.
Okay. So it's already, there is already a lot of infrastructure for it in place.
Yeah.
Actually, when researching for this, I actually found that even in nature, like you have your decaying manure that produces ammonia as well. Obviously, smaller concentrations.
Of course.
But there is some, so you can make ammonia in your garden. Easy. And
but the great thing is that the world's almost set up for us to use ammonia as a decarbonisation source. There's import terminals, there's production plants all over the world, there's ships already there to transport
I think in Rotterdam they already have the facility.
A huge import terminal there.
In the US there are a couple of them.
Yeah, they've got a big pipeline in the US and in Europe especially there's a lot of ships and terminals and they're building even more.
Also I know that in the Middle East they're building lots of facilities for that, to supply energy.
Certainly,
Yeah. Let's look at this safety thing.
Yes. So we touched on this slightly in the comparison slide.
Yes.
But as I mentioned, it's a really, really small amount of concentration of ammonia where it's dangerous.
Can you somehow explain that? So like we're sitting in this room and then we get a ammonia leak here.
Yes.
So that means like how much is dangerous to us?
So across the limit in terms of what we're allowed, obviously, ideally you'd have no ammonia whatsoever in the same room. But the limit in terms of what we're allowed across an 8-hour period is 20 to 25 ppm. So anything
parts per million.
Parts per million.
Okay.
Which is a very, very tiny amount.
Okay. And I think you can smell it even.
You can, but you don't really want to get to the point of smelling it.
Okay, so you want to get that before.
So you'd rather, that's why having gas detectors are so important.
Okay, so that means and what actually happens when we have too high concentration? How does it knock us out?
It just for your respiratory, as you can see the image here. The respiratory side of it is incredibly harmful. You'd have to get someone a medical person on to explain that side.
Okay, but it does affect the cells.
It's very dangerous
not only
for
us.
We don't want any of it really.
Okay, all right. Okay. And obviously there's the flammability part, which is between 15 and 33%. But you have to reach a certain concentration for that to even
exactly.
happen.
That's what flame detectors are still.
So I know we're here to talk about the safety of that.
Yeah.
And there you go. Where is it? You have the layered model.
Yeah. Right? So this is a way we like to show the layers of technology that's required to ensure you've got a safe strategy for an ammonia plant. So we use 3 combinations, makes it much easier to understand. So the ears, so we have an ultrasonic detector to listen for a gas leak. We have the smell, so various technologies to smell the concentration in terms of the technology side of it, and then also to see the flame as well. So you have to have a layered approach to ensure that a leak is detected and therefore.
So Jack, this is incredibly interesting. We're going to look more into this, and now we're going to do something which we've never done on Hyfindr Tech Talks. Bit of magic, because you didn't come alone.
No, I didn't.
So, are you relaxed?
I'm ready.
Ready for this? Okay. Yo! Here they are.
Where did they come from?
Well, thanks for dropping them in.
No
worries. These are the sensors that can do the hearing, the seeing, the smelling.
Exactly, They all have their own purposes.
Yes.
Should we dive in?
Please introduce us to these buddies one by one.
So I think it makes sense to start with this one here.
Okay.
This is called the Observer.
The Observer.
Yes.
So
what it does is it's effectively a microphone.
Right.
So it measures in decibels.
Okay.
So if you just go like that, you can see the decibels changing there.
All right.
So this is a very high quality microphone, but when you have a pressurized gas like hydrogen, like ammonia, when you have a leak, a rupture, it emits an ultrasonic sound that we can't hear, but this device can.
Okay, so it comes out like this squeaky.
Like that, but you can't even hear it.
Right. Okay, so this hears it and then does what?
So you normally have to have at least one different type of detector going off to emit. So it would cause a pre-alarm.
Okay.
But if you had multiple going off, then it verifies that it's a leak, and it would cause whatever the customer needs, whether it's a a shutdown
and so what do you call this again? This is
an observer, but it's an ultrasonic gas leak detector. So quite ultrasonic gas leak detector.
Okay,
so quite long-winded, but it's incredibly important when it comes to
observer eye.
Observer eye, exactly. Yeah.
Okay, cool.
This little device gives you a test as well. So it emits an ultrasonic sound to ensure that that's working correctly.
Okay. So that means it can make that sound and then
this little device here and test it to make sure it's working correctly.
Okay, cool.
Yeah.
Very cool. It is quite heavy.
You're struggling early.
Yeah. Okay, so which one's next?
Yeah, so we have the smelling detectors, which are these two here.
Those two.
Yeah, so either side, so we'll bring this one forward
so
first.
Bring forward first, okay.
Yeah.
All right.
So press this here. Thank God there's there's nothing in the room right now, but this measures in LEL percentage.
LEL percentage.
Yeah, exactly, yeah. So
what is that? What is LEL?
LEL so is the volume percentage in a room.
So LEL was the lower
explosivity limit.
Okay, that was what we were talking about earlier.
Yeah, so comparing
was it
ppm,
4% for hydrogen?
Exactly, yeah.
Okay.
Yeah, so usually you'd have a.
So on this dial, I would see the 4% basically. I was like, okay, now it's time to run.
No, so what this will say is if it's at 1% volume, that would be 20. So for hydrogen, for example, which is 4% where it gets to the explosivity limit.
Yeah.
So at 25% LEL, that's at 1% volume because it's a quarter. Does that make sense?
Okay.
It's easier to use that analogy rather than ammonia.
Okay.
So there's two different types of sensors. So this is a catalytic bead sensor because that measures in percentage. So that works by producing. There's two beads in the sensor. One's active, one's a reference.
Yes.
One has a catalyst in it, so it burns the active bead and sends an electrical resistance, and the amount of electrical resistance is proportional to the concentration.
Okay.
So if it burns more, there's more gas.
Yes.
Burns less, there's less gas.
So the beads are in here.
Correct. Yeah. There's two different types of technology when it comes to point gas detection.
So where does the gas go in?
Up through the bottom.
Up through the bottom.
Yeah.
Okay. And then and this is actually feeding in there, and then it shows.
Exactly. Yeah.
Okay.
So as I mentioned, this is an LEL percentage detector. So a catalytic bead measures in percentage. So it's more for large scale leaks. Using hydrogen as an example.
Yeah.
The lower explosivity limit of hydrogen is 4%. So at 4% volume, it becomes explosive or flammable.
Okay, but so we had it for ammonia. So this is now LEL, not ppm.
Yeah, exactly. So ppm uses an electrochemical sensor, so a different type of technology.
Yes. Okay.
So,
but you could put a ppm one here.
Yeah, exactly. Okay. Yeah. So you could have two here.
Put here.
So you could have.
I can have two. You can stick one on
so you could have a hydrogen one here and ammonia one here, and so both measuring.
Both
gas.
measuring LEL or ppm.
Either or, whatever you like.
All right. Okay.
But yeah, for an ammonia, you'd want to measure in ppm because I mentioned it's very toxic at lower concentration. So you'd want a ppm, which is an electrochemical sensor for that.
Okay. And so this one could do that job.
Yeah.
So this one could, at some point you would see that rise, and at some point we would also smell it, and at some point we would probably feel the biological effect.
Yeah.
All right. Okay. So this is a good warning guy in terms of the.
So that's point detector. So the gas has to travel to that sensor to give you a
gas has to come here. Okay.
Yeah.
All right. Okay. Well, I guess the other one was listening.
Listening. So it's got a.
It doesn't have to
range.
be there.
Exactly. Whereas the gas has to be here to give you concentration.
Right. So you mentioned that one's also on the smell side.
So this is a laser actually.
Oh yeah. Okay.
So a laser detector.
Can you take? Can you take it up? Okay. Oh, there you go. That's a.
Also quite hefty.
Okay, so that's a laser. Okay, so this can move back and forth. Okay, just to protect it.
Sun shield there.
Sunshade. Yeah. Okay, you don't want the sun shining.
It's like a little cap for the.
Can we get that in the camera here? Okay, yeah. So that's how it looks from the front. Okay.
Yeah. So you'd have a transmitter and a receiver. So they look exactly the same. You'd have them maybe 100 feet apart, whatever it is, whatever area you're covering.
Yeah.
But the difference is that. This is trained, every gas that's measuring has a specific wavelength.
Okay.
And so what it's doing is using the laser to check for that gas with a specific wavelength to cross the path of the laser.
Okay, so there would be like So this would be like one
Yeah,
side
and
of
I'd
it,
have one
and
there.
you would have the other one. Yeah. Okay.
Exactly.
And then there will be this laser going from
Either so, transmitter and
from me to you?
receiver,
Okay.
so sender
Okay.
and receiver.
And which
effectively.
one? And depending on how let's say the reflection of the gas is, or what?
Yeah. So if a gas,
what changes when the laser goes through it?
yeah, good question. So, so say an ammonia gas, because this only measures ammonia, not hydrogen.
Yes. Yeah.
So ammonia gas travels in between the laser with that specific wavelength.
Yeah.
And it absorbs the wavelength of the laser.
Okay.
And then that slightly dims the laser. And then how much that laser dims is the concentration of that gas crossing the path.
All right. So that means for example, the distance between you and me, which is not so big now, but if we go further apart, there would be more room for gas to come through. Yeah. And it will sort of, maybe collide with more or less atoms
exactly.
of
Well,
ammonia on the way.
The way the gas cloud behaves is it spreads as it leaks further. There's a high concentration. So say you have a 100 ppm gas cloud traveling from the laser, and that's spread across 1 meter, then that's still 100 ppm meters. Whereas if that's across 2 meters, then you multiply the distance and the concentration, and that will therefore be 200 ppm meters. And so that's the unit of measurement when it comes to these type of detectors.
Okay. And then you have to determine the different levels at which you trigger.
Of course,
alarms.
So that's all done when it comes to speaking with the client and deciding
how they want to set up
they want to set up there.
Okay.
So.
Well, we have a bit of a diagram here, so you can see. Yeah, you mentioned there are two. So
exactly,
we have the transmitter here.
So the design of the face enables this to have a wider area of coverage.
Yeah.
So that any misalignment is counted for.
So you have the transmitter that's sending the laser.
Yeah.
And what happens then?
And the receiver is then checking constantly to see if there's a gas. So this is trained exactly for ammonia in this scenario.
Yes.
So it can be trained for any type of gas that is measuring.
Okay.
So each gas has its own wavelength.
All right.
And it's constantly checking to see if
wavelength in terms of when the laser hits it, it changes.
Exactly, yeah.
It changes the wavelength of the laser.
Yeah, well, it absorbs.
It
absorbs the wavelength of the gas that's crossing it. But so it's only specific for that. So you'd have, if you were measuring a different gas, then you'd be looking at a different type of wavelength in the laser path.
Okay.
So this diagram shows exactly what happened and the points that it's checked. So as you can see, the filled in bit is where the ammonia gas has followed through that laser and it's absorbed. And this is therefore checks it at 4 different points.
So that means the black.
The black one is no gas.
No gas. So normal laser just passing through, everything fine. Yeah.
But then when it's absorbed, you get the.
Okay, so when there's now gas in, then that absorbs part of it, and then that changes, and now it's on the receiver to see. Oh, I see these changes.
And the magnitude of that absorption relates to the concentration of the gas. So a larger absorption means there's a larger amount of gas across a larger area.
Yeah.
And so then that's how you provide a usable measurement that you'd go back to.
So a large amount of gas would just absorb.
So there'd be a large.
What happens when someone walks through it? Don't they block it completely?
Yeah, that's right. It does block that completely. But so that's why you make sure we've had scenarios of people building walls in between a laser before.
But does that trigger an alarm, building a wall?
It would trigger a fault, that there's something blocking in it.
Okay,
It will constantly check it. If someone's walking across it, then there'll be a momentary lapse of...
so the alarm is only looking for the distortion. It still wants to get laser, but the distorted...
Exactly. It's looking for the absorption, for that gas. It's specific to that. So,
okay. And you said it depends on the concentration, how much is absorbed, and with that you can measure the concentration.
Yeah, so the way we measure the specific amount of gas and the cross distance is by using a unit of measurement called ppm meters.
Okay.
So obviously, because ammonia is so dangerous at lower quantities, we have to measure in ppm.
Okay.
So right now,
ppm meters means parts per million
meters.
In the meter. Sort of.
So for example, in this scenario, you have a 100 parts per million gas cloud, and that's spread across 1 meter.
Right.
And so that's therefore 100 ppm meters.
Okay.
So you simply multiply the distance by the concentration, and that's how you measure the gas.
Okay.
Compared to like 0.1, where it's just ppm, just measuring the actual.
At that particular point.
Yes.
Yeah, you have
but
to.
here's because of the distance, you have to counter into
You don't literally you don't know where exactly this cloud is along the. You just know
But you know there is a
this
cloud of a certain concentration
Okay.
and a certain distance in there,
Okay.
and it will tell you that.
And what happens when it's spread across a longer
Yeah,
area?
so for example, in this scenario,
Yeah.
you have a smaller concentration, so 50 ppm, half of that.
Yeah.
But because it's spread across 2 meters,
Yeah.
it's the same unit of measurements. This is why it's both 100 ppm meters.
So
it's,
this is
multiplying, yeah.
This is 50 ppm in 2 meters is 100
Yeah,
ppm and 100 ppm in 1 meter
Exactly,
is also
yeah.
100 ppm meter.
yeah.
Right.
So
okay.
that's how it works.
And that's when so obviously you set your alarms to trigger at a certain
Yeah,
ppm meter
Correct.
level so that it
Yeah.
compensates. Okay. All right. Okay. Understood. Now I get it.
Now you know.
Well, thank you very much, Jack, for sharing this. Now
That's
we know
okay.
all about open path gas detection with lasers.
Happy to help.
Right. Okay. So thank you. This is now.
No worries. Put it back on its stand.
Yeah, or just drop it there. I think it's going to be.
Yeah.
So then we've got one more to go. Yeah.
We certainly do, and this is the last layer of detection.
The last layer. Okay.
Yes. So this is a UV-IR flame detector.
Mm-hmm.
So the key thing is that
UV-IR.
UV, so ultraviolet infrared.
Okay. All right.
So when hydrogen and ammonia, both of them burn,
Yeah.
they burn within those two wavelengths. So
Yeah.
the UV and the IR wavelength.
Okay. They emit that kind of UV rays.
Exactly.
Or light.
Yeah.
Okay.
So
okay.
the reason why you need both is that when you
UV
send
and IR, they are the ends of the
either side,
visible
yeah,
scale.
exactly,
Okay.
yeah.
So okay, so you do they both emit UV and IR?
Exactly, yeah.
All right. Okay.
And so that's how you check to see if there's a flame there. So the sun, for example,
Yes.
it emits light in both sides of it, but you have to check with both sensors
Yeah.
to configure and confirm that there is an ammonia or a hydrogen flame.
Okay. I know you have a. We had a diagram to show that a bit earlier. So this is the normal visual. This is where we normally see the visible light.
This is the visible light and sun's
Infrared
radiation.
region.
So as I said,
region.
it will emit it on both sides of it, which is why you need both sensors. So you've got an infrared up there, ultraviolet in the middle, and that's constantly scanning for both of them to be ticked off. They're like, yes, there is a hydrogen or ammonia flame. And so this is how this works.
Okay, can you just show where's the infrared one?
So infrared just there,
Yeah.
and ultraviolet just there in the
There.
middle.
Okay.
So,
So that's basically constantly watching.
constantly watching. So there's a field of view,
Yeah.
about 125 degrees. This will actually be pointed down. You'll have this
Okay.
very high up, above any sort of structures.
Okay.
And then it'll be focused on ignition sources. So I mentioned both of them are flammable. Hydrogen is a lot more, it has a much larger flammability range. Ammonia, a smaller window, but is still flammable, can still cause an ammonia fire.
Yeah.
So you'd have them pointed where there's electrical components, ignition sources, which can transport which can create the flame. So when and it's in the flammability section, and then the flame's produced, that's when that's triggered.
Okay, so that means now we have all these different ones set up for listening here, and basically you've got a full guard system in place. And here you brought a simulation of how that looks. Yeah. Well, what are we seeing here?
Well, I think it's one thing to be looking at the detectors, but understanding where they fit in a plant, I think is quite useful.
So this could be like an ammonia plant,
or So what we can do is we can create a gas leak. There we are.
So these are all pressurized.
Yeah, these are valves. So we'll just use this one as an example.
Okay, and then you have a leak here.
Yes, exactly.
And do you have any sensors already?
Yeah, well here we go. Here's the first sensor.
Okay, so that's how you install it. Just switch them on. And
Exactly. Yeah, easy as that.
Easy as that. Okay.
So what you'll normally do is to ensure there's no false alarms. You'd have obviously the layered detection of detectors, but then you'd also make sure that you have multiple going off simultaneously to trigger a shutdown. So you'd have a pre-alarm that will notify you that yes, there's a leak. But then you'll have this connected to a controller, which will then trigger either ventilation or a complete shutdown. You've got dangerous gases in the vicinity. You want to make sure that there's definitely a leak before you close everything down.
So the ones you just put in.
So that's
these ones.
No. So this is a point detector.
The point detector.
Yeah.
Okay, yeah.
So
the gas has to
travel there to be able to create that alarm. So they'd also use an open path detector, which will then cross that boundary between the laser. So you can see, as I mentioned,
So
two of these.
This
So there's
okay.
transmitter.
So point detector, open path detector.
So as you can see,
this is the laser one. What was it called again? The
laser ELDS.
ELDS. Okay. So you have them mounted.
So
like this
so as you mentioned, now two are being triggered as that. Yes, there's a gas leak, and that's then causing an emergency shutdown.
Yeah, the point detector is going at 68%, 69%. This one is detecting 65 over this distance. Okay,
but the key thing is when you have an outdoor environment, obviously you might have wind.
Yes.
And so the ultrasonic gas detector, which is the first line of defense, this is where it's really key and where it's really beneficial to someone with an outdoor plant. As what we can do, we can simulate a wind condition, a blowy wind condition. So we can blow a wind coming from this area here. Yeah. And as you can see here, there's nothing being alarmed. So it's completely negating the effect of the gas.
It's literally blowing over the laser line.
No, it's blowing, this way.
This way.
So it's coming away from the gas detector and from the laser detector.
Okay, because they're both standing behind that.
Yeah, exactly.
All right.
As the valve's just there that's leaking. So this is where...
So it's all blown away?
And it's negating the effect of these detectors. So this is where the ultrasonic comes in really key because it's not affected by any wind conditions.
Right.
It's trained to know what exactly an ultrasonic gas leak is, so a pressurized gas leak.
But isn't wind noisy in that sense?
Well, what it's got is an artificial neural network technology inside of it, and it's trained to know what's an ultrasonic gas leak and what's wind or a compressor or a helicopter or anything going past.
Okay, so where would that go?
So this would go either side, and as he's mentioned here, because it's not affected by the wind, both of them are going off because this is within 28 meters range, and that's therefore triggering an emergency shutdown because it's clarifying that yes, there's two of them going off and there's definitely a leak.
So two of them, meaning even two of the same kind can trigger them. Okay, so
exactly.
Okay, but so if it's only one of them wouldn't, but since it's that there, okay.
Exactly,
right. Okay, and then so can you turn off the wind and let's see what happens when the others go in? Okay, so here it's going normal again.
So that's going straight and
these ones are detecting that.
They're all
these
going
ones
off,
are going up. Okay, so there's now.
But this is an ideal world where the gas that goes straight up and everything's detected straight away. But realistically, we live in a world where it's unpredictable. Gas leaks and the spread of gas is unpredictable. And we can't simply say place a detector above a valve which is a leak path, and then it will.
Can you turn that off? The leak. The leak is okay. So all the detectors are now back to zero.
So this is why it's so important to have a combination of technologies when you have especially an outdoor environment.
Okay. Super interesting. Thanks very much, Jack. I think we've run out of time. Can you just tell us? So now we're seeing this, and you already mentioned this has neural networks,
artificial neural network
inside. Where's this all going? Are we gonna? Can you tell us the future of safety in ammonia? Yes.
Well, as I mentioned at the start, green ammonia is going to be a key cornerstone of the clean transition. We've adapted, it's an industry we've supplied for decades, as I mentioned. We've adapted to these new applications, so combining both hydrogen and ammonia. We'll continue to adapt to these applications, but at the end of the day, physics doesn't change. The characteristics of these gases remain the same, and therefore the applications to ensure the safety of those plants will remain the same. So we'll be there to assist with a clean transition using these technologies to ensure that everything's safe when it comes to it. And
so
that's a key part of it.
So that will help basically ammonia also grow as an energy provider.
And so everything you hear in the news is going to be positive about how it's helping that transition.
Because you've
got the safe there, and the risks behind it are being negated by the use of these technologies.
Perfect. Thank you so much, Jack, for
sharing
so much insight. Thank you for bringing them along. Thanks, guys. Nice. Go off to work. And thank you for watching. This has been an absolute pleasure. Thank you for watching Hyfindr Tech Talks. Please follow us or look at our LinkedIn channel as well. We have a site, hyfindr.com, where you can find all these components and get in contact with people like Jack so that you can use them for your ammonia or hydrogen or whatever application. Thank you for watching. Have a good day.
Perfect. Thank you. Cheers.
Thank you.